Right, on air. Sir, you can start, sir. So you can start,
Hello,
sir.
everyone. I'm Subramanyam, working in School of Physics, University of Hyderabad. Today's topic is quantum information. So what I'm showing here is something I downloaded from internet. It's called Borromean rings, where you have three rings, blue, red, and green. In the absence of, let's say, green, red and blue are not entangled, which means that you can take away blue to the, and then without disturbing red, and vice versa. This is what is called three-body entanglement. So the quantum envelope is what is shown here. So these are my collaborators over the last 20 years. Been working on these fields. Professor Arun Lakshmi Narayan at IIT Madras, Anand Jha, H. Vanare Sekad Ghosh at IIT Kanpur. And these are the four students this I've shown here. DDB Rao, Sunil K. Mishra, Saikat Sod, and Vimlesh Kumar Vimal. They've graduated in these years and then are working in various places, currently shown here. And they basically worked on various aspects of entanglement information, quantum dynamical processes, state transfer, spin models, generating non-local Bell states, Loschmidt-Echo, state revival, etc. Many of these topics are actually related to quantum dynamics of spin chains and quantum information of spin chains. And these are the two students who are currently with me. They've just joined, Sadaf and Madhurima. So this is the plan that I have for today. What I like to do is that first few minutes, maybe 15 minutes, for continuity, let's review ingredients of quantum computer. So we'll talk of single qubit, pure states, mixed states, how to control them, gate operations, many qubit states. When you interaction, what happens? Basically, there'll be entanglement, decoherence, and so on. Then I'll go ahead and discuss at length evolution of a quantum state. So this will lead to various basic concepts of information and uncertainty, entropy. They're all same things, which we'll see as we go along. And then QDP is the quantum dynamical process. This is how you evolve a state, by doing a process on a state and it evolves. Then we focus on non-unitary evolution and quantum information, and this will lead us to the main topic of this presentation today, where we'll talk of local quantum operation, CP/TP maps, quantum channels, fidelity, quantum mutual information, private information, data processing, and so many other things. So some of the reference books, they're listed here. The first three, which is by Nielsen and Chuang, the first one, and the second one is Bennett, Casati, and Srini, and the third one is by Deservoir. These are all very nice books, which you can, all of us students can pick it up, and with a little bit of quantum mechanics background, they can go ahead and read. They'll review all aspects of quantum information, computation, starting from classical information theory, quantum information, various aspects of quantum systems, Hilbert spaces, and so on and so forth. But these are all somewhat old books in the sense that Nielsen Chuang is about 20-year-old, and maybe the other two maybe about 10 years old. More recently, somewhat more mathematical books are these two in the middle, namely the book by Waltros and Wilde. They're substantially more mathematical, but still they're quite well written and easy to understand given a level of mathematics expertise. And lastly, quantum theory concepts and methods by Perez and modern quantum mechanics Sakurai. These are very nice books. In fact, these are older books. Perez's book came around 97 or so, and Sakurai, of course, even before. This is just quantum mechanics. But these books are strictly for physics, maths, graduate students. Have lot of mathematical expertise.
Recording in progress.
To understand these books. All right. So let's start with the part one, ingredients of quantum computer. Basically, you have qubits, Q gates. There'll be entanglement. There'll be decoherence. why should one be interested in a computer of qubits? The one word answer would be that there's a quantum storage, which is huge storage, and there's a huge speed up. And qubits, there are many physical realizations in the course of these lectures. Last 2 weeks, you have heard many such realizations. We'll also talk 1 or 2 of them. Coherent, incoherent states, how to prepare, we'll talk, and interaction. So this is, we'll talk at a very, very basic level to pick up our conversation. First, quantum computer. You know that quantum computer is a computer, and it is a network of qubits, just as we have a classical computer with a network of bits. A classical bit, 1 bit, is basically there are 2 states, let's say 0 and 1. So what you can do is that you can denote one of 2 numbers. Let's say you have 2 numbers, x and y. I can denote state 0 as x, standing for x, and state 1 standing for y. So which means that you have a bookkeeping device of these 2 bit states, 0 and 1, for standing for 2 numbers. It could be 2 numbers or 2 different entities. Similarly, you have 2 classical bits. These are the states listed. And you can denote each one of these states. It can denote 1 of 4 numbers, let's say UVW, and so on. Now, if you have n classical bits, that means you have 2 to the power of n states, and can denote 1 of 2 to the power of n numbers. This is the straightforward understanding that we have. Now, the same thing we can say about a quantum bit. Let's say quantum bit, unlike the classical bit, which has only 0 and 1 states, it can be any one of these states, A0 plus B1, and AB can be any complex numbers, infinite number of set of quantum numbers. So which means that there are infinite number of states, though it's a 2-dimensional Hilbert space, in the sense that there are 2 basis states. Let's say these are the basis states. The 2 classical bit states are the basis states. And now you have linear combination of these states, and any number of states you can construct. Which means a quantum bit can store 2 numbers A and B of infinite set of numbers. So if you want to store A and B complex number, I'll construct a qubit, which is this. So that qubit actually has these 2 numbers inbuilt. Now 2 qubits you have going ahead. You see that you have this sort of state where you have first qubit in this state, second qubit in this state. There are infinite number of possibilities, and they're all product states, because you have a state for first qubit and the state for second qubit. Similarly, you have this sort of state where you have A times 0, 0 of this, and B times 1, 1 of this, and so on and so forth. Now, this is also infinite number of such states are there, but they may not be product states. They are non-product states, can be. If you have n qubit state, is characterized by 2 to the power of n complex numbers. Why? You have n qubits, so you have 2 to the power of n classical bit states, which are the basis states. Now, for every basis state, there is an amplitude. So you have A1, A2, A3, and so on and so forth, 2 to the power of n complex numbers. In other words, if you have n qubits, the general state will be characterized by so many complex numbers. Now, Hilbert space have huge place. How big is the storage? It's, as I said, n qubit mixed state. If you look at, it's a density matrix. We said already dimension is 2 to the n. So the density matrix will have 2 to the n cross 2 to the n number of numbers, which is 2 to the power of 2n numbers. For n equal to 10, the dimensionality is 10 to the 3, and the numbers will be 10 to the 6, because it's a matrix. Now, for n equal to 30, the number is 10 to the 9 is dimensionality, and the numbers you have to manage is 10 to the 18. Now, if you want to store 10 to the power of 18 numbers, you need classical storage of billion 1 GB pen drives. So all of us have pen drives in our pockets. So everybody contributes 1 pen drive of 1 GB. Then you will be able to store 1 state of a n qubit state. So which means basically you are exhausting all the storage available on the earth for storing 1 state of a 30 qubits. That is because you're using a classical storage to store a quantum state. But other than that, let's say you have a quantum bits, chip of 30 qubits, you can store 10 to the 18 numbers just on 30 qubits. So which means that if you have a Q chip with N30, then you can store 10 to the power of 18 numbers. So that is how is a gigantic storage, a quantum storage of quantum chip. Now look at some sizes. Gigabit classical chip, we have a pen drive which is roughly 1 centimeter across, roughly, or even 1 millimeter sometimes. And basically you have small spins here, either 0 or 1, each one of them, and that is how you get it. And if you have a 30-bit micron Q chip, because you need 30 bits, then the size will become, instead of 1 centimeter, will become 0.1 micron. So here, each one of the bits actually is a quantum bit, so you can actually manipulate superposition of states. Now you see that if you want to store 10 to the 18 numbers, you need 10 to the 9 centimeter of physical space if it's linearly placed, or if you put it in a two-dimensional array, you need so many square centimeters, 0.1 square kilometer. Now, if there is a gigahertz classical processor, which means that it does 10 to the 9 operations per second, to read in these numbers 10 to the 18, you need 10 to the 9 seconds. Remember, you have 10 to the 18 numbers, right? So you need 10 to the 9 seconds to read in those numbers. So that is roughly takes 3 centuries. But if you have a quantum chip, to read in this 10 to the 18 numbers, you have to just manipulate these 30 qubits, which means that if you have a quantum chip with 30 qubits, by just manipulating the 30 qubits, which will take some time of the order of, let's say, 30 times some operational time, you will be able to read in these 10 to the 18 numbers. So that is how the speed up. So what can be done only in 3 centuries on a classical chip, you can do in a few nanoseconds using quantum operators. Now, let us look at a quantum computer flow chart. It is not different from a classical computer. Roughly what you have is you will have some information, and then you will process it, various steps, you will do various operations, and then you get out, read out. Whatever your computation you've done, you read out. That's a classical computer. Similarly, you have quantum computer. So you have prepared the state, which means that you need a physical apparatus, let's say qubits you need. So typically you have electron spin as a qubit, or nuclear spin as a qubit, or photon polarization as a qubit, or two low-lying states of trapped atoms, ions, or as qubits. These are the various physical realizations that are being used so far. And then you have basically have many qubit state here. So all the information is coded into this state. And then what do? You do a series of operations called gate operations, or transforms, or unity transforms. So basically you do many transforms, that is computation. And if it's still coherent, you go back and do more computations, and finally you do a measurement or something and read out. So if the qubit decoheres, then you have to start the computation again. So it all boils down to how much is the decoherence time for qubits. So I copied this from Nielsen and Chuang. This is around 20-year-old data. So various qubit systems, nuclear spin, decoherence time is of this order, 10 to the minus 2 to 10 to the 8 seconds. The operations you can do within for operation is 10 to the minus 3 seconds. And the number of operations you can do before it decoheres is around anywhere from 10 to 10 to the 14. For the trapped ion, these are the numbers. And for electron as spins, let's say in gallium arsenide, you have 10 to the minus 9 is the decoherence time. And the operation time is 10 to the minus 13. So you'll be able to do 10 to the 4 operations. Similarly for cavity QT. All these numbers are tables have taken from Nielsen and Chuang, which you can check yourself. And of course, this is 20-year-old. Now things have changed, maybe slightly changed, not very different. Now, expertise needed to build a quantum computer. I've just listed the topics which I came to my mind. It needs all sorts of things. You need classical optics, quantum optics, condensed matter physics, quantum spintronics, you need nanoscience, you need material science, you need chemistry, and you need information theory. And also you need electrical circuits, gates, hardware, interface technology, algorithms, mathematics, foundations of quantum mechanics. You cannot escape this, and the measurement. The measurement means measurement theory you have to know. So what we'll do is that in this talk, we'll focus a little bit on information theory and foundations of quantum mechanics and understand a few concepts. Instead of showing various experimental results, I'll focus more on understanding simpler concepts in terms of simple like 1 qubit and 2 qubit states. So if you build a quantum computer, the promise is that you have a memory storage which is gigantic. It's a huge speed up, and there's a security protocol. If you have a quantum computer, of course, all the classical security is compromised, but you have quantum security protocols. And then you can solve finite time, non-solvable quantum simulation problems, and also do quantum simulation. This is a promise. There are a few implementable quantum algorithms which have already been there for years now. And some of these are listed here: teleportation, superdense coding, Deutsch algorithm and its extensions check if a function fx is uniform or balanced. All these have been implemented. Grover search, wherein you search n items to find the item you want, and that is done in order root n steps. Quantum Fourier transform, which is you can do in log capital N square number of steps. And this is you should contrast this with the best classical Fourier transform, fast Fourier transform, which is n log n order. And factoring a number in this order, these are all discussed in some of the books I've referenced. Okay. Now, let's now go to part 2. So let's get a little bit more technical. Now, till now we have been talking generally of this and that. So what we'll do is we'll now get down to one bit, classical or quantum, and see how to prepare a coherent, incoherent superposition states using Stengel capitals. You can analyze them, how to control a bit, block sphere representation, and so on and so forth. If you have any question, we can stop for a minute.
TSAT team, are there any questions?
All right, so let's move ahead. Okay, so now we'll get a little bit more technical now. So you have a qubit, and we said that qubit can be in a superposition of many states. So let's say this is a state, this is a Schrodinger ket state. If you write it's a ket, so this is called a ket state. So it's alpha up plus beta down, up and down are some two basis states. Then you can say the density matrix for this, the density operator is basically put the ket here, psi and bra. This is a density operator, and if in a matrix representation, it will become a matrix. Now, for a pure state, these two are equivalent. You can work with psi or rho, which is this, and this is a projection operator. So basically, any let's say you're interested in an expectation value of some observable, let's say A in this state psi, you can go ahead and sandwich this A between this state psi here, left and right, and you'll get it. Or you can take rho, multiply by A. So there's a matrix representation for A and there's a matrix representation for rho, and multiply them and take a trace, which means sum over all diagonal elements. So these two are exactly the same for pure state. If you do the trace here in the orthogonal basis, let's say psi and phi, then the psi phi overlap is 0. Then since I took a diagonal basis here, psi and phi, this is the orthogonal basis. So then this trace will be psi psi here with rho A here in the middle and phi phi in the middle, and you can see that this is 0 because psi and phi are orthogonal, which means that this expectation value will be simply same either when you do take it from Schrodinger ket state or density matrix state. Now, these are all pure states. This is a coherent superposition. That is, you take these ket states up and down and superpose using probability amplitudes alpha and beta. So the probability of the state up in this state psi is alpha mod squared. But superposition is done by probability amplitude. This is called coherent superposition. Now, you have other states, which are mixed states, which is the incoherent superposition of pure states, wherein you have, let's say, rho for an up state. Let me call it some state psi 1 with a probability P1, and another state psi 2, which is also a pure state, psi 2, and the density matrix corresponding to that is psi 2 and P2 here. So P1 and P2 are now probabilities, P1 plus P2 equal to 1. Now, for such a state, there is no Dirac state description, because you cannot say that with probability P1, this is a wave function or the state, and this is probability P2, this is a state. Right? So here there's a description only as a density matrix. So in this talk now, we'll only discuss states represented as density matrices. So rho is a pure state, is a projection operator of this kind. If it's not a pure state, it's a mixed state. It will be a decomposition in terms of pure states with probability P1 and P2 and so on and so forth. So this mixed state, for this, when P1 and P2 are non-zero, you cannot write it as a state chi, ket and ket bra. Why? If you can do that, that means this state, let's say psi 1 and psi 2 are orthogonal, then the eigenvalues of the density matrix are P1 and P2. Now, if you say that this is equivalent to a state of this kind where the eigenvalues are 0 and 1, so you're actually changing density matrix eigenvalues from this P1 and P2 to 1 and 0. By a unity transformation, you cannot take this mixed state to a pure state and vice versa. A mixed state has at least 2 non-zero eigenvalues, and a pure state is only one pure state is needed, and it is a projection operator. And there will be an orthogonal state for this. So you have a state which is orthogonal to state psi. Whereas a mixed state is not orthogonal to any state. In fact, all states it has to overlap within this two-dimensional Hilbert space. Now, Stern-Gerlach apparatus. What you do here is a project spin states. So let's say you have a stream of particles coming in one after other very slowly in a state psi of this form, alpha up plus beta down. Now it goes through an apparatus called Stern-Gerlach apparatus, wherein you have basically an inhomogeneous magnetic field along that direction. Let's say up and down are z eigenstates, sigma spin sz eigenstates. Then you have two possible values for sz, h by 2 or minus h by 2. Now, because of this inhomogeneous magnetic field, so the particles having projection up only, they will come through this side, and then the probability is alpha magnitude square, and the state is up. And the dispersion is such that the particles with sz equal to minus h by 2 will come slightly differently. The slightly different gate here, probability is beta mod square. So this is a pure state here, which is the probability alpha mod square, and there is a pure state down here with beta mod square. So given a state, a pure state here, then it goes through these operators and you'll get up or down states with these probabilities. Remember that every particle passing through this SG apparatus will come either here or here. It doesn't come as a superposition of this. Now, result for each particle is either this or this, and it's truly random in the sense that one particle comes. I will not be able to predict within quantum mechanics whether it will come here with h by 2 or minus h by 2. It's just not possible. Unlike, let's say, a random process of, let's say, tossing a coin where you have two states up and down, coin will come flip either up or down. And there we'll also say it's a random process, but it's a lack of knowledge of variables. We'll say that actually it is not random in the sense that if you know the coin has so many other degrees of freedom inside, so many particles are there. If you know the behavior of all the particles, then you can predict whether it's coming up or down. But lack of knowledge, we'll call it a random process, and that is fine. But here, it is not lack of knowledge. It is simply not possible to predict because in quantum mechanics, there's no rule which says that which particle will come here, which particle comes here. But if, let's say, series of particles come, let's say a million particles comes here, come through this, then roughly alpha magnitude square fraction of that will come through up, and beta magnitude square fraction will come as down. So, which means this is truly a random process. So one more thing is that you cannot distinguish non-orthogonal pure state, let's say psi and up here. Let's say the input state is psi, let's say it comes up because the probability alpha mod square is there for to come as a up particle, so it will come. Now if the input particle is up also, it will come here. So by looking at the result, you will not be able to say whether the input state is psi, which is of this form, or just it is a alpha equal to 0 state, which means orthogonal pure states cannot be distinguished. Now, what is a pure and mixed state in terms of this? If it's an unknown state, then I'll put a magnetic field along some direction n. Now, there are two fractions with h by 2, s dot n, and s dot n equal to minus h by 2. There's a fraction f plus and f minus. For every direction n, these two fractions are non-zero. Then I'll say the input state is mixed. On the other hand, there exists one direction at which one of the fractions is 1, other fraction is 0, which means that it has to be a pure state. Okay, this is a similar thing that I have shown here. So you can prepare a coherent or incoherent superposition at will. So let's say you want to prepare a coherent superposition, a pure state. What I'll do, I don't know what is coming in here. I'll put a magnetic field in some direction. Let's say this is the state I want to prepare. This corresponds to one particular direction magnetic field. I'll put it and I'll collect this state. Let's say all the particles coming in this and falling here. So this ensemble is represented by the density matrix, a pure state, namely alpha up plus beta down. On the other hand, if I want to construct a mixed state, what will I do? I will take, let's say, one of these states and let it go through, let's say, another SG apparatus in magnetic field along Z. Then you'll see that it will be either plus half or minus half. Let them all come, and then I'll put it in one box. Then alpha magnitude square is the probability for getting up state, and beta magnitude square is the probability for down state. They both are coming inside here. So now this ensemble is represented by mixed state because the particle is either an up state or a down state with different probabilities, and this is a mixed state. So obviously, without interaction with outside, I cannot change from a mixed state to pure state and pure state to mixed state. So one more thing is that a pure state is going to mixed state means that's called decoherence, because we have a coherent superposition state has gone to incoherent superposition state. That is what's called decoherence. And later we'll see that entanglement means also decoherence. All right. So this is a general one qubit state. So this is various ways you can represent. So as up down are the basis. As I said, there's a probability for up state for Q, and 1 minus Q is the probability for the down states. This is the way normally information theory people would like to write the mixed state. And you can view that as a thermal state, like in condensed matter physics. What you have is a spin half particle, and you put in a magnetic field. So when you put a magnetic field B along some direction, then the two levels split. The energy difference is 2B times mu B. And if you look at the finite temperature, then this is a state of the system, which is e to the minus beta Hamiltonian H, which is given here, divided by e to the minus beta A, which is the Helmholtz free energy. In other words, the probabilities for occupying this state and this state will be determined by this beta, which is 1 by kBT. And the relation between these two approaches is shown here. Now, once you have this thermal state picture, now A is the thermal, Helmholtz free energy. So thermodynamic definition of entropy is dA by dt with a negative sign. You can do it on this state, and you'll exactly find this, which is what phenomenal entropy of this state. So this is one way of looking at it. Another way would be that since this is a two-dimensional Hilbert space, so you have operators, identity operators, sigma x, sigma y, sigma z operators. They'll all come with some coefficients, and the coefficients are fixed, arranged in this order. For this to be a density matrix, place rho equal to 1. That's why the identity will come with 1/2. Then sigma x will come with px, sigma y will come with py, sigma z will come pz, some numbers. So there's a vector p, which is the polarization of the state, which is simply the expectation value of this operator in this state rho. Now, this p vector will have a magnitude p and the direction. So let's say this is the direction and this is the magnitude. If p is equal to 1, that means it touches the surface of the sphere. This is a unit sphere. And that's the pure state. All pure states will lie on the surface of the sphere here. And if p is less than 1, this becomes mixed state. So that means the length of the vector is less than 1. Now, correspondence of this capital P, which is the polarization strength, with this picture is this 1 minus 2q magnitude is that. And with this picture is beta times magnetic field is tan hyperbolic of that is this. This is the connection between all these three pictures. It doesn't matter which way you look at it. This is the simplest way of looking at it. Now, if you want to look at it as a thermal state or want to look at it as a density matrix with polarization P. And how to manipulate a qubit? So basically what you have is a two-level system. So as I said, you put a magnetic field in some direction, then the two levels have energy difference, call them up and down. And by connecting, so there's one diagonal operator, that is, these are eigenstates of the diagonal operator, let's call it sigma z. And there's an operator which will take you from this to lower state to the upper state, let's call it sigma plus. And there's an operator which will take you from upper state to lower state, sigma minus. So that's how you get sigma x, sigma y, sigma z. And that is what is a qubit. So which means that if you have two states, it becomes a two-level system. It only becomes a classical bit. But on the other hand, if you have access to transition operators taking from this state to that state and also bring it back, all of them together, that is what is a qubit. That means you should be able to control that operation. So at low temperatures, the state will be like a pure state, it will be here. And at a high temperature, it will be like a thermal state. You can actually access any state, pure state like this, by putting a coupling to the applied magnetic field. And you can couple to an electromagnetic wave field to stimulate absorption and emission, which means that it will go from here to here and here to here. So which means you have a control of this qubit, pure or mixed you can generate. And this has been perfected for years now. Difference between one qubit pure and mixed state. This is a slide which what we have been saying last 10 minutes is summarized here. So you have a pure coherent superposition state, which is like this. Now you have mixed coherent state. I've just taken alpha magnitude square for the probability for up here and beta magnitude square probability for down state. Then the eigenvalues here, of course, 0 and 1 because it's a projection operator. And here the eigenvalues are alpha magnitude square, beta magnitude square because up and down states are orthogonal states. So the entropy here is 0. Entropy here is non-zero. The von Neumann entropy we defined in the previous thing. Now, if you look at SZ expectation value, sigma Z expectation value, that is the eigenstate of, this is up and down the eigenstates of sigma Z, SZ. So basically, simply it means actually this is something small mistake here. It is alpha magnitude square minus beta magnitude square. In this state also you get the same answer. In this state also you get the same answer. But if you look at SX expectation value, for this state you'll get alpha beta star, and for this state you'll get 0. Similarly, SY also will be non-zero here. SY will be 0 here. Namely, sigma Z eigenvalues, measurement values will exactly be same in these two states. But if you measure sigma X expectation value or sigma Y expectation value, they are different. And as we said, this is a pure state. By doing a unity transformation on this, I can take this state to up state. There exists a unity transformation taking you from this alpha plus beta down ket state to ket state up. Whereas here, there's no unity transformation that you can do which will take you to this up state. Because if that exists, then we know that unity transformation preserves eigenvalues. Once this happens, the eigenvalue here is 0 and 1, whereas here is alpha magnitude square and beta magnitude square. So which means that this is not possible. So here, this is an eigenstate of an observable. So that means there's a unique way of preparing. If you want to prepare an up state, all I have to take is sigma Z eigenstate as a construct. Stern-Gerlach apparatus, apply the field along Z direction and take a particle coming from one gate, and that is the pure state. Similarly, this state is also eigenstate of one particular direction. So every pure state is an observable eigenstate of an observable. And there exists an orthogonal state. For up state, there is a down state. And because it is a pure, there is an orthogonal state, you can form a measurement basis. For instance, up state and down state you can use for doing orthogonal projection measurements. Whereas you cannot do that using these pure mixed states. All right. So we'll get a little more technical now. So you have any questions?
Sir, I believe 1 or 2 questions are already posted in the Zoom box.
Yeah. So let me try to get that. All right. So Ramya from Hyderabad is asking, who will be impacted the most by quantum computing in the short term? What business sector do you think will be impacted first by large scale computing? Actually, I have no experience to answer this question. And there are several other speakers in the previous week and the earlier part of this week, and maybe later they will be able to answer this. I'm not really an expert in this business sector, what they're doing. Okay, there will be a large number of sectors will be affected. That much is clear. Okay, the first thing, if someone has a quantum computer with a big chip, okay, let's say 30, 40 qubits, truly, then everybody should be scared. You and me and everyone. All your bank account, passwords, everything will be compromised, right? So you'll have to run and remove all your money from the banks and keep it. Okay, someone, Somik from Khammam. Does quantum computing, in your opinion, affect data storing? If yes, how? Can you elaborate on data storage and improvement by quantum in storage scheme? Actually, the storage business, I'm not expert in this field. So what we try to do now is that we'll get a basic understanding of how these things are done. Actual storage, is not easy. Even if you store, let's say, 10 to 18 numbers in 30 qubit chip, how to retrieve is not easy. Okay, so it's a different ball game together to actually do that actually. And one thing to say that I have a 30 qubit chip and it can show so many numbers. These two are independent. I hope I answered a little bit. All right. So a little bit more technical, let's get. And the idea is that the part 3, we have to now get used to 2 particle systems, 2 qubits and many qubits, and then entanglement naturally comes. And then fourth part, I will go into information. And the information is the way actually practical use of this, all this we are saying. All right. So in this part coming up, we'll talk about bipartite entanglement, pure and mixed states. It's somewhat more mathematical than previous parts. There's a Schmidt decomposition is a very well suited, gives you understanding of pure state entanglement. And then we'll talk of quantum gate operations, which are very simple operations, and evolution of many qubit state we'll see, and interactions, how they create entanglement decoherence. All right. So the gentleman shown here is Einstein. He actually thought about quantum mechanics at for a long time, and he was not happy with the quantum mechanics because of these 2 reasons. What he was saying is, a physical theory cannot violate realism and locality. That is the thing. So quantum mechanics seems to actually violate realism and locality. Realism means the following. Let's say you measure you have a small rod with you, let's say 10 centimeters or so, and you measure it using a scale, and you find that it is 10.1 centimeter. Now, does the rod have that length when you measure, just before you measure, and then your measurement reveals it? Yes, that is what you mean by real. So the value that you measure is the real. So the quantity has that value and you are measuring it. Your experiment should reveal. That is what is realism. But remember what we said to quantum spin. Before it goes through the apparatus, it doesn't have that spin value. Let's say magnetic field is put along some z direction, sz equal to h by 2. It doesn't have that value because there's no way it can have. So which means that quantum theory doesn't seem to work with the realism for the parameters that the variables you're measuring. And locality also is a problem because what you do, let's say you have 2 particles, one particle sitting here in Hyderabad and another particle sitting in Mumbai. Now, for some reason, they're in entangled state. Now, it looks like that if I do something on particle A in Hyderabad, it seems to affect particle B at Mumbai. So, which means that the locality seems to be not guaranteed. Okay, so when you do some thing on some locally some variable, it should affect only that. It should not affect things sitting, let's say, very far. So quantum mechanics doesn't seem to basically respect this, and that is why Einstein was deeply uncomfortable with that. For years, he was arguing. Finally, anyway, it has been proved that quantum mechanics does violate realism and locality, and that's how it is. Quantum states, non-local features they have, though. Quantum mechanics itself is local theory, but quantum states have non-local features, they can preserve it. For instance, entanglement between A and B, when you take A and B very far away, they still preserve. And of course, realism is not there. What more, there's a very basic difference is that classically, if let's say a system which has 2 parts A and B, classically, if entropy of A is non-zero and entropy of B is non-zero, then the total entropy will be non-zero. Let's say entropy of B is non-zero and entropy of A is non-zero. Then I'll say the total system entropy is non-zero. But quantum mechanics, it is not true. You can have entropy of A non-zero, B non-zero, but AB is 0. Of course, entanglement is ubiquitous. I've just written down some things. For instance, you have this parametric down conversion in optical systems where you emit entangled photons. So there are 2 photons emitted. One photon goes in one way, another one goes. So they are in entangled state. And similarly, high energy gamma ray, you have electron-positron that can decay into electron-positron pair. It's entangled. This is a 0 momentum state, 0 angular momentum state. They are entangled. So electronic shells of many electron atoms, they show entangled states. For instance, look up this book, Frank Jensen, Introduction to Computational Chemistry. They are entangled states of these many electron atoms. In photosynthesis, energy transfer between light harvesting complex and photosynthetic reaction centers seem to show entanglement. So entanglement in Fana-Matthew-Olsen complex has been observed. And transitioning to non-physics or philosophy, there's a universal law postulated by the philosopher Gurdjieff, the law of 3 and the law of 7. Basically, what they import is that the entanglement between various components, that is essential for group work. That is a tagline for Gurdjieff and the disciples. Also, in preserving esoteric knowledge, let's say in the ancient times, let's say you have a big book like Mahabharata or something. So make replicas and pieces, make it into million pieces and distribute among citizens. No subset of people can corrupt the message. And if it's corrupted, then Entanglement can be used to revive like in a hologram. But then there's one problem is that if we have distributed this knowledge to all the people and the whole set decides to destroy it, of course, that knowledge is not worth anyway. Okay, so when say somebody's entanglement, what comes to our mind is spaghetti. This is a photograph I've taken in my home about 20 years back. So this is a spaghetti. It looks entangled, but actually there's no entanglement here. Why? The way we make spaghetti is that we take water and put the strands which are on untangled state. They look like entangled, but locally they look like entangled. But I can take one strand and then smoothly take it out to infinity without S, so it can be separated. So which means it's not entangled, though it looks like entangled locally. So let's talk of entanglement of strings. So what I'm showing is, let's say two strings, one is red and one is black. If they're like this, they're not entangled. But let's say the red one is in a loop and then black is also in a loop, it is not entangled. Then the red one is gone like this and black one is gone like that. Locally there's something entangled, but smoothly I can take the black one to infinity without upsetting the red one, so there's not entangled. Similarly, this also is not entangled. I can take this black away easily. However, you take these two, I make a loop of red and also make a loop of black such that there is an entanglement here. Now, if you try to take black to infinity, then red also will come with me because there's entangled. Similarly, the red is there and black has gone 2 times through and this is also entangled, but this entanglement is slightly more than this. And similarly, this has more entanglement. So these are the two-party entanglement in strings. This is a three-body entanglement in strings. So now red, green and black. So if black were not there, then red and green are not entangled. And if green is not there, still black and red are entangled. So which means that there's a there's a three-party entanglement, but black, red and green are not entangled in the absence of black. But here, if you see, okay, look at the rightmost thing. This is the same as this. And you see that if you remove the red one here, then you see that the green one is a ring, so it can come through. So that means in the absence of red, blue and black and green are entangled. Similarly, if the green is not there, also red and black are not entangled, you can see easily. Because this loop will come up and then red will come off. So this is a three-party entanglement. This is what I showed in theorem in ring in the beginning of my talk. From Wikipedia, I downloaded and showed. All right. Now that is the classical strings. Now quantum strings. So you have a bipartite system. Let us say A and B are two different systems. A can be any number of qubits and B can be any number of qubits. For the time you think of A to be 1 qubit and B to be 1 qubit. So the Hilbert space is constructed, let's say, from the direct product states of A and B. The basis I've constructed on direct product basis. Then the state of the system can be a coherent or incoherent superposition. Let us look at first coherent superposition. So there is a pure state of AB. So it's a pure state is a projection operator, is a psi, and the psi is now in the AB state, right? So which means that there's a basis state U for A and the basis state V for B, and it comes with an amplitude psi UV. So this is a coherent superposition of this AB state. Similarly, you have mixed states. This is just analogous to what we discussed for 1 qubit. Rho AB, you take a P1 probability with psi 1 is a joint state AB, P2 probability with joint state psi 2. So that's a mixed state. All right. So now let's say you are interested in an observable of, let's say, part A. So that is, I have an operator O, expectation value of that A, this deals only A. Now that is basically, now as I said in the beginning, so take this state rho AB and multiply by this operator O and trace. This trace is on A and B, both states. Now, since the operator has nothing to do with B, what I'll do is first I'll do the B part trace. When I do a B part trace with rho AB, this will give you a reduced density matrix of A, and that's what I call rho A. So which means now this operator expectation value seems to be OA, rho A trace. This trace is now in part A. So you can do this, or you can do this as the same thing. But what I'm trying to say is rho A stands for the reduced density matrix of rho AB. And as far as all operator expectation values of A concerned, rho A suffices. So which means you can always get all the information about part A by doing this trace with rho A. Now, remember rho A stands for the state of A in bipartite state rho AB, but there is no guarantee that rho A represents a pure state, even if the parent state rho AB is a pure state. So parent state is, let's say, pure state like this, but there's no guarantee that rho A represents a pure state. That brings us to entanglement. So basically, I have state of this total system, let's say, is a pure state, and this part I'm calling A, and this part is next is B. Now, if I look at rho A, which is trace B of this rho AB, now this is a mixed state, can be mixed state. So if there's if rho A is a pure, then I will say there's no entanglement between A and B. Entropy of subsystem is 0 because rho A is pure. On the other hand, rho A is mixed. That means there's an entanglement between A and B, and that is given characterized by the entropy, which is non-zero for A. So all I'm trying to say is, if A and B are entangled, then the reduced density matrix of A will have an entropy which is non-zero if parent state is pure state. Now, if you do a unity transformation on this state, rho AB, then the state will become psi to, let's say, some state phi. Then the entanglement property of psi and also the unity transform can be different. So this is, for instance, a state I've written which is not entangled, because in both these pieces, state of B is up plus down, which is a product with the up state for A. So it's an unentangled state. But this state I've written A and B are entangled, so which means that state cannot be written as a part A state and part B state as a direct product. All right. So entanglement between spatial parts in a pure state, basically you have this state. This is shown just now, and this is these are entangled state and these are non-entangled state. Now, when you have this state, basically I'm looking at the reduced density matrix and its eigenvalues, right? So which means that if I do a unity transformation, which is only a product of unity transformation of A and B, then the eigenvalues of A of reduced density matrix will not change, because I'm doing a unity transformation which is only on part A, let's say. Okay, which means that will not change the entanglement. So basically, if a unity transformation U, which is UA times UB, if I do on psi, then phi and psi will have exactly the same entanglement properties. Namely, a direct product of UA times UB unity transformation, which is local transformations, product of local transformations, it will not change entanglement properties. However, if there is a unitary operator which cannot be written as a product, that can change the entanglement properties. So one more caution is, let's say you are doing it UA times UB on this psi, but let's say A and B are big systems. A has some 10 spins and B has some 10 spins. Now A, I and BJ, I spin from A and BJ, J spin from B, their entanglement can be changed by doing this transformation. Why? Because this is a direct local transformation as far as A is considered as a whole and B is considered as a whole. But if you look at A1 and B2, for instance, the entanglement between this A1 and B2 can be changed through this transformation. All right, some more examples. A bipartite state of this form, rho AB is rho A times rho B, and rho A can be mixed or pure, rho B can be mixed or pure. This is an unentangled state. This is a direct product state. Now, if you take one such thing with a probability P and another with a probability Q, some other product, gamma A times gamma B. Gamma A is also density matrix for A, gamma B is density matrix for B. Even this is not entangled, because this is what is called a LOCC state. Namely, this can be built using local operations and classical communication. For instance, A is sitting in Hyderabad and B is sitting in Mumbai. Then he will prepare a state with probability P and phones him. Then the B has already prepared some state rho B. Now, if with probability Q, A is preparing a state gamma A and then B is preparing gamma B. So, but through communication using, let's say, telephone, they can actually construct this joint state, and this has no entanglement because this has been constructed using local operations and classical communication. This state can be entangled or can be direct product, right? So for this one pure state, now if it is of this form, then it is entangled. Now if you have these two pure states, both are entanglement, but now we have superposed incoherently. So state psi, which is an entangled state of two parts, and phi is also entangled, but now if you superpose with this, now this state can have some entanglement or maybe not entangled. So you have to see how it goes. So if you have a multipartite state, that means you have n qubits, then a pure state will be of this form. So S1, S2, Sn is the state of each qubit. For instance, ith qubit is in state, let's say Si, we'll take 0 and 1, and so on and so forth. So this amplitude phi depends on all these values. So there'll be 2 to the power of n number of complex numbers in built-in. This is what we started in the beginning. So such a state, which is a pure state of n qubits, can exhibit a variety of entanglement distribution over its part. So it's possible that 1 and 2 are entangled and 1 and 3 are not, and 3 and 5 are entangled and 3 and 4 are not, and so on and so forth. The distribution can be very, very different, and it can have a distribution quite different from other states. Moreover, when you do a unity transformation of this state, which is a global transformation, then the distribution can also be changed. Okay, maybe I'll skip this. Okay, this different ways of entanglement. Maybe I'll skip this also. Okay, so let us discuss bipartite entanglement in pure state. It's the Schmidt decomposition. So basically, you have, let's say, two parts A and B. A has Hilbert space 1 to n, state I, and B has states 1 to m. Let's say m is smaller than n. Now, a pure state of AB will be shown like this. So take a state from A, I, take a state from B, J, that comes with phi is an amplitude. Now, J goes from 1 to m because the m-dimensional Hilbert space. I goes from 1 to n, the n-dimensional Hilbert space. Now, Schmidt decomposition is a simple way of understanding that entanglement between A and B is given by the entropy of, let's say, density matrix rho A and or density matrix rho B. So they will both have the same entropy. That means they will have same eigenvalues. To show that, first understand that rho A comes by doing a trace on B, and that is basically phi dagger. This phi ij is a m cross n-dimensional matrix if I view. Then phi times phi dagger will be n by n dimensional matrix, and that has information about A. So this is a reduced density matrix A. Similarly, if you take phi dagger phi, this will be m by m matrix, and the eigenvalues of that will give me determine the entropy of rho B. Now, how to show that the entropy of these two entropies will be same is very simple. So what you do is here, since I have two different sums here, first look at the sum over I with phi ij I. So understand that this is a state of A, right? And that depends on J because J label is there. So I'll put J tilde, that is the state coming from this of A and state of J. Now J goes from 1 to m. Now you see that here exactly m states are there for both the parties, A and B. B of course is J orthonormal basis, but J tilde, they may not be orthonormal. So what you have to do is you have to do Schmidt normalization, orthogonalization you have to do. So basically, you have basically n states coming from A, they may not be orthogonal. So you use a diagonal basis of marginal of B. That means you take the diagonal basis of rho B here, then you'll see that this will be also orthonormal. And then take the norm of that, keep it outside, then the phi AB of this form. Now you see that J equal to 1 to m exactly like this, and now you have normalized state of A and normalized state of B, orthonormal basis, and Nj is the number that comes for each of these basis states. Now eigenvalues of rho A are basically Nj whole square, a magnitude square, magnitude n1 eta magnitude 1 magnitude square, eta magnitude m square. There are so many of them. M will be non-zero, and 0, 0, 0, and so on and so forth. Whereas eigenvalues of B will, of course, eta 1 magnitude square up to eta m square. What I'm trying to say is, for A, the dimensionality is bigger, namely n is larger, but m eigenvalues are coming here. The other ones which are not come basically are 0. Now, if you look at the entropy of SA, basically you take this eigenvalue and times log eigenvalue is a minus sign, sum over all eigenvalues. That is for A, and for B is also exactly the same. So which means, but this procedure, you can see that if you have a pure state, then S of row A is same as S of row B, and that is used as the entanglement between A and B. So it is non-zero only if two non-zero Schmidt numbers are there. These numbers are called Schmidt numbers. Eta 1 magnitude square is a Schmidt number, for instance. If there is only one Schmidt number non-zero, means basically that will be 1 or 0. So that means you'll get entropy 0 for the sub part. And if two numbers are non-zero, then you'll always get a non-zero entropy for A and also for B. And that is the entanglement between A and B. This is the story as far as the pure state is concerned. Now, mixed state is slightly different. Okay, let us discuss the purification of mixed state first. So you have psi AB. We said that this is of this form in the previous transparency. Basically, I state from A and J state from B comes with phi ij. So this is the pure state, and rho A, that is the state of A, is basically phi dagger. It can be mixed. So which means that joint state AB is pure, but part of the A state is mixed and B state is mixed. You can use this conversely. A mixed state of A can be thought of as a pure state of A and E. That is, let's say you have a row A. I can think of a pure state phi AE, and this is the pure state density matrix, and trace over E. When I do, I'll get a row A that can be mixed. So for every density mixed state of row A, I can always think of a pure state phi AE is the environment, if you like, and if I trace out the environment, I'll get a rho A. So if you like, phi AE is called purification of A, rho A. So which means phi AE can be written like this. Exactly, you have seen that before for AB. And now this will give you, if you eliminate E, then you get rho A, which is this, which is a mixed state. So which means you can always associate a pure state in 2D dimensional Hilbert space for every D-dimensional mixed state. So if rho A is a D-dimensional state, then all I have to put an environment D dimension. So basically I have 2D dimensional Hilbert space now here. All right, D cross D basically. So this is actually D squared actually, because D for A and D is for B. Now, bipartite entanglement in a mixed state is not such a easy thing to understand, because A and B are not entangled. This sort of state we already said that is a LOCC state, because A and B can communicate with each other through classical communication and prepare the state. But there's another problem. Let's say there's a state which is not of this form. It can be entangled, but there are many ways to construct a mixed state as a pure state decomposition. For instance, rho AB is of this form, and another decomposition of this form. So where the probability Q1 and Q2, and then states are phi 1 and phi 2. So the concept of entanglement of formation is that, so let's say that this is entangled. So take the entanglement of here with weight P1, and the entanglement of this state, this is actually psi 2. And then that comes with probability. So you can take the average entanglement weighted with the probabilities of each pure state. What I'm trying to say is, this is a pure state, there's an entanglement between A and B, so take that, and then weight it with P1 and so on and so forth. So that is what is called a weighted average. But then that weighted average will give a number, but then you have many different ways of representing. Each decomposition will have a set of pure states with probabilities. So what you do is, you take a minimum of all possible decompositions, and that is what is called a entanglement of formation. But the only thing is that this minimization cannot be done. See, any minimization process you have to do basically for all possible decompositions. So it cannot be done in general, but it has been done for 2 qubit states. That is, A is a qubit, B is a qubit, and it has been done by Wouters in 1999. So the entanglement measures for bipartite is that SA rho A for a joint pure state, psi AB, for concurrence and entanglement of formation for joint state, like just now I said, the Wouters formula. The Wouters formula is complicated. It is CAB is basically maximum either 0 or this. Lambda 1, lambda 2, lambda 3, lambda 4 come with square root with lambda 1 with plus sign, and lambda 2, lambda 3 square roots will come with minus sign. Where these are decreasing order of eigenvalues. Lambda 1 is larger than lambda 2, and so on and so forth. These are the eigenvalues of rho tilde, which is the time reverse state of rho AB. This is the formula of Wooter's. And also there's the Perez criterion, negative under partial transpose. That is, you do a partial transpose only, let's say, part A, and then if it becomes the density matrix has some negative eigenvalues, then the negativity measure you can take of define this way. And similarly, there are many other entanglements like localizable entanglement, CMI entanglement, which is conditional mutual information based, bound entanglement. So many measures are there. We'll skip all of them. And this is the one view graph I would like to show how you change the state. Basically, you change the state of a let's say qubit by doing a unity transformation. You can do a Z gate, which only means that 0 goes to 0 with +1 and 1 goes to -1. And Hadamard gate, basically 0 goes to 0 +1 and 1 goes to 0 -1. And the C0 gate, which is on 2 qubits, 0 0 beta 1 1 state will like. This state will go to 0 0, whereas this state will go to 1 0. This is a control NOT operation as a control as the first qubit. And the first qubit in state 1, the second qubit changes, flips. So like this, you can have many qubit gates. Each one is like one gate. Basically, what they do is they transform one state to another state. A state input state is mapped to another output state. Similarly, this is the same thing as what I said before. And this is an entangling gate. So where you have up state, and this is a sigma z and sigma z of 1 and 2. And you can show that this will take you to this. And this is not a direct product state, it's an entangled state. Okay. So before concluding this part, what I want to say is basically an evolution of a single qubit is that a qubit in an up state can undergo an evolution, let's say time evolution, through unitary transformation, it can become a state plus. So this is a unitary operation. So the pure state remains pure state. This is what happens. You have a spin interact with a magnetic field. You can also have an open system dynamics wherein you have a time evolution incorporates both unitary and non-unitary aspects. Then the state up can go to, let's say, plus state with F plus and minus state with F minus. As we saw that Stengel-Lac apparatus, a state of this comes and then magnetic field in such that these are the eigenstate of that S dot n, then you will get this state. So by interacting with, let's say, environment, like here Stengel-Lac apparatus, you can actually undergo a unitary or a non-unitary transformation for 1 qubit and similarly for 2 qubits. And let's focus on these 2 qubit ones, the same state that we showed before. You have a state up, acted upon by this unitary operator and goes there. Now, if you look at on the left side, rho 1 equal to rho 2, this is a 2 qubit state, 1 and 2. So rho 1, rho 2 is basically up state. So here, the entropy of rho 1 and entropy of rho 2 is 0. Both of them are pure. Whereas here, the output state, you see that rho 1 and rho 2 are same. The rho 1 is cos square phi is a eigenvalue for up state, and sin square phi is eigenvalue for the down state. So that means now you have two eigenvalues here, sin square phi and cos square phi, and it will give you non-zero entropy. Whereas the eigenvalue here, 1 and 0, will give you 0 entropy. So you see that a pure state has gone to a pure state as far as the 2 qubits are concerned. Joint state is concerned, has gone from pure to pure. But then if you look at part 1 qubit, first qubit or the second qubit, you see that it has gone from, let's say, pure state to a mixed state. So which means that the whole is undergoing a unitary evolution, basically coherently evolving, whereas parts decohere. So this is what I mean that this state has no entanglement. This has got entanglement between 1 and 2. On the other hand, 1 and 2 actually decohered. So the entanglement is between part 1 and part 2. And also it means that part 1 is decohered. So entanglement is on one side of the story and the other side of the story is decoherence. These two are exactly the same. If a 2 qubit state goes from a pure state to pure state, then it's a unitary evolution as far as the joint state is concerned. But for the part 1, first qubit or second qubit, it is a incoherent or non-unitary evolution. So this is a quantum state transfer through spin chains. Basically, we have, let's say, start with all up state and then one spin I put in this. Basically, I put in the alpha beta complex numbers coded at t equals 0 in the mth qubit and let it evolve through some spin Hamiltonian. Later at time t, I'll recover that state from here with some fidelity. This can be done, and it looks like it happens that conservations in the spin models and invariances, they actually affect the state transfer fidelities. And presence of entangled pairs of spins makes recovery better and larger fidelities. And not only that, not only the state can be transferred, even the entanglement can be transferred. For instance, let's say there's an entanglement between 1 and 2 spins, that also can be transferred to another pair at a later time. For instance, we have done long back simple studies. I've taken some 20 spins, and then in the beginning, the first pair is a Bell state, maximal entangled state, and evolve it, and they'll see that wherever this white patch is there, that means that pair is entangled. So you see that it goes up like that, and after some time, entanglement is there everywhere. So the pair here is a little entangled, there's a pair here entangled, and so forth. We call this quantum mat. This is using a Heisenberg interaction. And this is a global interaction. One spin is entangled with the rest of the spins, and how that evolves using a kicked Ising model. And you see that various parameters are there. For some parameters, there is a large average entanglement, global entanglement. All right. So now we'll go to part 4. Any questions? All right.
Sir,
Isha from Hyderabad. My question is, a highly entangled quantum system synonymous with a strongly correlated system? Okay, the answer is no. Normally, when you say strongly correlated system, you mean actually diagonal correlations. Okay, so it turns out that diagonal correlations will decrease the entanglement. For entanglement, what you need is off-diagonal correlations. There are some papers you can read. This is Kamlesh from Karimnagar. My question is, how does C0 gate work? So basically, it is a 2-qubit gate. So you have to basically know the state of control bit. Based on that, you operate on the other bit. So it looks like a 1-qubit state operation, but it depends on the second qubit state, the control bit state. And you can read Nielsen Chuang. They discuss it very simply. Preeti, she is asking that it is possible for 2 respectively closed systems to be entangled. So it is not possible. So if you have, let's say I have one spin. Okay, now I have lost the question was. Just 1 second. Yeah. So let's say you have one spin, which is in a box, which is impenetrable. That means interactions cannot get in. Similarly, another spin also is in time. So then each one of them will have only a unity transformation. So to start with their direct product states, they will forever be direct product states. On the other hand, the wall is not impenetrable. Let's say some small possibility of, let's say, things can be transferred, for instance, like slightly open, then eventually they'll get entangled if there's an interaction. All right. So any other questions?
Sir, at 11:37, sir, at 11:37, I hope you have got one more question from Mr. Surya.
Yeah. Okay, I'll answer that question a little later because now we have the main part, which is the information. All right. So classical or quantum Shannon theory, that is what is called information theory. So first we have to understand the information. So binary random process, let's say you have, which means that 2 values the random number can take. The process is X. So it has 2 values, X1 and X2, with probability Px1 and Px2. So P of X1 plus P of X2 will be equal to 1. That is the probability process. Then, so basically you have only one probability. One is P and another one is 1 minus P. Then the Shannon binary entropy is defined as minus P log P base 2 and 1 minus P log 1 minus P base 2 with a minus sign. So basically the probability of the first one with the log of that, probability of the second one times log of the probability with a minus sign, that is what defined as the Shannon entropy. Now if you plot this as a function of H as a function of P, then you see that it is a peak at P equal to half, wherein you see this is 1 and this is 1, a half, and then add up to 1. And for all other values, it is smaller. At P equal to 0 or P equal to 1, it will be 0. This is the definition of binary entropy. Similarly, you have, let's say, many possibilities. Let's say X1, X2, X3, X4, various possibilities.
And then where probabilities are associated with this, you can have slightly P1 log P1 minus P2 log P2 and so on and so forth. Now, you have a joint distribution. Let's say you have two processes, X and Y. There's a joint distribution PXY, which only means that this is the probability that X will take the value, this value, and Y will take this value. What is the probability? That's called joint probability distribution. From this, I can get marginals, which means that you take this probability and sum over all possible values of Y, that will give you probability for X. And similarly, sum over all possibility of X, then will give you marginal R, so basically is reduced probability density for Y and X. So this will give me H of X, and this will give me H of Y, and this will give me H of XY. So these are the Shannon entropies, corresponding probability distributions you can calculate. And mutual information is defined as H of X plus H of Y minus H of XY, which means the marginal distribution will give me X entropy and Y entropy, and take the difference of that with the total entropy. And this is what is called the mutual information between X and Y. And this is 0 if the joint distribution is a product distribution. If the joint distribution is a product, then HXY will be exactly same as HX plus H of Y. And this determines the channel capacity, and we'll see in a minute more. So I've just given you definitions here. Is it clear that you have a probability process, and then the probabilities matter for the Shannon entropy, and the actual variables do not matter. X1 could be, let's say, red, and X2 could be black, two values of colors, or X can be winning a match, and X2 can be losing a match, okay? And so on and so forth. What matters is the probabilities. Now, can we now talk of Shannon entropy of a qubit state? So we have discussed quantum bit. So now quantum bit is given in a state. So now can we think of a Shannon, associate the Shannon entropy to this state? The answer is okay. Let us see. So let us take this qubit state, which is in this state. I've taken 1 plus P is some probability P and sigma Z. This is a state. Now let it go through a sigma this Stern-Gallak apparatus with a magnetic field N. N is some direction such that you have theta and phi characterize N. So theta makes an angle with the z-axis, and if you project that unit vector in the xy plane, it makes an angle phi with the x-axis. That is the notation we are using. Now, this is a sigma z eigenstate with plus 1 plus p by 2 and 1 minus p by 2 are the probabilities. But then, since it's going through this state, then you'll get two values, h by 2 for s dot n and minus h by 2 for s dot n. This is the probability p. You can easily compute is 1 plus p cos theta by 2. So basically, this is the overlap of this state psi with the upstate magnitude square, and this will be same. Now, by changing this number, so basically I got a probability p. So that means you'll get a h of p. So h of p with n1 is the direction 1, and then h of p you get another number with n2, and so on and so forth. So what I'm trying to say, for every direction I'll repeat this. So for every direction I'll get two numbers, p and 1 minus p. I'll get the Shannon entropy for that particular result. And then you'll get many numbers, the set of infinite numbers I have by changing the magnetic field in all directions. But then if you look at, let's say, the magnetic field in the direction of sigma z, that means in the diagonal basis, then obviously the eigenvalues will be 1 plus p by 2 and 1 minus p by 2. So one eigenvalue is lambda, 1 plus p by 2, other one will be 1 minus lambda. Right? Because now n is z here, so that's why this. So now this also will give a Shannon entropy, and that will be contained in this because I've varied in all possible directions. That will be inside this. So all I'm trying to say is the lowest of all these numbers is what you get here. So that means you look at this h 1/2 plus p by 2 cos theta, that is here. When theta equal to 0, I'll get this. So this. So now this is always greater than equal to this. Why? Because if you take h of 1/2 plus yx, remember that the Shannon entropy was peaking at half. Now, if you go away from half, then it will be smaller and smaller. Now, for x same, y less than 1, then if y is non-zero, then it will always be greater than equal to 1/2 plus x. All right? So, which means this is true. Which means the minimum of all these Shannon entropies that I can get, that is what is called Fonheim entropy, is basically the Shannon entropy in the diagonal basis of the density matrix. So if you want to associate a Shannon entropy to a quantum state, they're not one, there'll be infinite number of them. And one of them is the least of all of them, that's the Fonheim entropy. Basically, the density matrix eigenvalues determine the entropy. Now, this is the entropy of measurement and mutual information. So, as I said just now, you can do a measurement in a different basis and they'll get a P and 1 minus P probabilities, and H of P is always larger than or equal to S of rho. We just now said that. This equality holds only if the measurement is done in the diagonal basis. And that minimum value is what is called von Neumann entropy, which is minus rho log rho trace. Now, this is similarly entropy of preparation. So that means now density meter you want to prepare. Again, you can prepare many ways. As you said that a mixed state can be prepared in many different ways. So again, if you prepare it in the diagonal basis, then the entropy of preparation will be S of rho. In any other basis, it will always be larger entropy that you will put in. That is, you have non-orthogonal basis states also you can take and do that. And similarly, quantum mutual information. Remember, we defined a mutual information classical distribution Pxy. So if you have a density matrix rho AB, then you have quantum mutual information defined as the partial density matrix rho A entropy of that SA and the entropy of B minus S of rho AB. Is analogous to the classical mutual information. And this equals twice the entanglement of a pure state. If your rho AB is a pure state, this is 0, and these two are same, and that is the entanglement. So for a pure state rho AB, mutual information, quantum mutual information is the same as entanglement measure. All right. So basically what we'll do next 5-10 minutes before going to mathematical description of this information is that qualitatively let's understand information, uncertainty, entropy. And then we'll ask what will happen if you do a measurement on that, all qualitative without going to mathematics. Okay. So information is what you seek. And when you seek information, there is uncertainty, then only you seek that I want information. And that measure of that is entropy. That let's say you have a somebody sitting in Mumbai, he's doing a coin, toss of a coin. So he has tossed a coin and the result will be either 0 or 1, depending on, let's say heads up is 0 and down is, tails is 1. So the result is 0 or 1 that I know, but I don't know whether it is 0 or 1. So sitting here in Hyderabad, I have a confusion, uncertainty, whether it has come 0 or 1. Since I need to know that, that means I need to get the information. Now, when you have probability P for head, then probability for tail is Q, which is 1 minus P. So there's a probability for 0 is P and probability for 1 is 1 minus P. Now, depending on the value of this P, then entropy, we already said the Shannon entropy, it depends on uncertainty and it goes from 0 to 100%. P equal to 0, then there's the entropy 0, and P equal to 1 also 0, and then P equal to half is the maximum entropy. So remember that P equal to 0 or P equal to 1, then sitting here in Hyderabad, I have no uncertainty about the result because I know that P equal to 0 means the result is only 1, right? And there's no uncertainty. So which means entropy is 0. So I don't need to get any information. So no information sought or gained. On the other hand, let's say P is close to 0.9. That means that result is always more probable that it is up than down. Then I know that more or less it's like a cricket match between Australia and India, let's say in 90s. Then I know that more or less Australia is going to win. So there's a little uncertainty, and then to remove the uncertainty, a little information is sought. Whereas if it is P is 0.5, that means the probability of winning and losing in half. That is the time there's a maximum uncertainty and I need the maximum information. So that is what is summarized by Shannon entropy. H of P is minus P log P minus 1 minus P log 1 minus P, and H takes value 1 only for P equal to half. And for H equal to 0, for P equal to 0 and P equal to 1, which means that to remove the uncertainty of some variable that I want to know, I need information. So when I say information, it is for the seeker. That's why I am seeking information to remove some uncertainty, and the measure of that is entropy. So this is a practical way of this thing, that information, uncertainty, entropy are all same things. When you have uncertainty, that is when you seek the information, and the measure of that is 1 bit of information means that you relieve uncertainty of the 1 bit. So the maximum is 1, That is, you take a log base 2. That's why it peaks at 1/2, and that is the case where both the states are equally probable. That is the maximum information I can get. Now, if P is close to 0 or close to 1, then corresponding information is also less. So if I want to know about this process, whether it's a head has come or tail has come, then that person has to convey that much information to me, and that information can be conveyed by one transfer of 1 bit of information. And the maximum information is 1 for 1 bit. So it's going from 0 to 1, and that is coded by this. Similarly, if you have many states, P1, P2, Pn, then this source coding theorem of Shannon, you can see that P1, P2, Pn by log n, the base n, if you take, and then this is the, no, not base, actually log n base 2 actually. This is what is a compression ratio of, you have, let's say, large text where each alphabet AI comes with probability PI, then how much you can compress, and that is given by this. So this is practically used when you write a file and compress it, because compression decreases number of bits to be transferred. All right. So now, what will happen to, let's say, evolution of the state? Evolution means that anything you do with the state, when it changes, that's called evolution. The spin state before, and let's say spin state after, and I'm doing a measurement. And this is a classical. So state is probability P up plus 1 minus P down. So the Shannon entropy of H of P. So before a measurement, this is what H of P, that is the information that I need, and that is the entropy associated with it. Now let's say measurement apparatus is only one measurement apparatus I have classically, because up and down basis, I'll either get up or down. This is the classical state, only one basis of measurement. Now, not knowing the result, let's say I've done the measurement, but I don't know the result that you got, then if I don't know the result, then no information is gained, no collapse of the state, uncertainty is intact, state in is same as state out. And no disturbance, in the sense that by repeating this measurement many times, you can actually get the distribution up is coming how many times, and down is coming one at a time. So which means that Shannon entropy of measurement H of P can be measured by repeated experiments. So since you can actually measure the input H of P exactly, so there is no disturbance. This process doesn't disturb the state. This is the classical thing. Only serious snag in the classical thing is that there is a security breach due to eavesdropping in the classical products of communication. Let's say this is a communication channel, and then this is going through that, then somebody can intercept this and gain the information, and without your knowledge, you don't even know that you have been tapped. So this is what I said, repeated measurement on identical prepared systems in identical setup, distribution can be measured, information of the input state can be gained classically. Now, knowing the result, of course you have done this. It's not knowing anyway that, so knowing the result, the state is collapsed, uncertainty is removed, because now I know the result. The result is up. The output state entropy is 0 because the state has come up, and there's no disturbance anyway because repeated measurement I can do. But you cannot know if the information is trapped or private. This is what happens if I'm talking to someone on the telephone. I don't know if somebody is listening in. There's no real way of making it out. Okay. Now, evolution of 1 qubit in quantum case. The spin state before, let's say again 2 states, H and T, and probability P here and 1 minus P. But remember, it's a qubit, which means that H and T are 2 basis states, but I can also do measurement in any basis I want. So let's say I do a measurement in an up-down basis, which is not the same basis here. Then I'll get 2 different numbers, Q and 1 minus Q. Here the entropy, Shannon entropy is H of P, and here the Shannon entropy is H of Q. So which means not knowing the result anyway, no information gained, and collapse is unknown, uncertainty is intact, output state different from input state because the measurement has been done. There's a disturbance in the sense that probability distribution change because H of Q is greater than or equal to H of P. But knowing the result, what will happen? I know the result now. So information is gained, but I don't know how much I've gained because H of Q is actually a different number compared to H of P. If it's the same, that means the information that is being sent, I've got it. Information I want to know, I have known. So I know information, but I don't know how much I've known. There's a state collapse here, uncertainty not removed because the state, I don't know complete information, and output state definite entropy is 0. And disturbance there is, because this disturbance means what? Probability distribution change. Here the probability distribution is P and 1 minus P. And here is Q and 1 minus Q for these 2 states I've chosen. So minimum of HQ is input Shannon entropy in diagonal basis equal to finite entropy. So for instance, if I do a measurement in HT basis, then I'll get P and 1 minus P, and I'll measure exactly the input measurement. And one plus point of this quantum this thing is, it is impossible for eavesdropper to go undetected. Impossible to breach security. Trapped information may not reveal desired information. Information is private, which means that if somebody is trying to listen, get the state here and get the information, then output the state, you'll not get H of P. If I'm getting H of P here, same as here, that I know that there's no breach of security. Now, how about a joint state? This is very important. Okay, either classical or quantum, let's say. So you have a joint state. This is the joint state. You have up for the joint state with probability P and down with 1 minus P. Now, entropy of the joint state is H of P because there are two probabilities P and 1 minus P. So entropy of joint state is H of P. Now, if you look at rho A, that is a state for A is also P up plus 1 minus P down, and rho B is also the same. So now entropy of A is also HP and the entropy of B is also HP. Now, let us say A gains information of the state by measuring. So here's A is in Hyderabad and B is in Mumbai again. So A has done a measurement on his qubit and then measured H of P and got full knowledge of his state. That means Shannon entropy is HA, HB same, but HAB changes now. Because he has done a measurement on joint state, though it's done on his state, but the joint state will change also. So A gains information about B also. But B has no information about the state because B has not done the measurement. So the only way B can know the information is that he has to phone up A and find what is the result, or he has to measure his own state. So some people say that when A measures, then the state of B is collapsed. Actually, that may be collapsed, but as far as B is concerned, he has not gained any information. Unless A phones and through classical communication channel tells you the result, B cannot gain it. And there is something called no signaling theorem. So which means that B, there's no way can B get information about his own system. It's a no-go theorem. B cannot know from measuring his state if A has done a measurement or not. So let's say B at a later time has measured his state. Can you figure out whether A has done already a process or not? There's no way of knowing. We'll elaborate it in the next view graph. If there's a dynamical evolution of the joint state post measurement, A and P can be distinguished. A does a measurement process, and then B later can detect whether he has done or not. A has done the process or not if there is a state evolution after the measurement. Okay. There is another issue which I wanted to say is that let's say you have a joint state. Now the state is unknown. If I do a joint measurement in, let's say, direct product basis. So direct product basis will be 0, 1, 1, 0, 0, 0, 1, 1. Each one of them will give probabilities. Now, each of the output state is unentangled. Input entanglement, if it is there, it is lost. Which means that by knowing the result of this joint measurement, I cannot figure out whether the input state is entangled or not. Now, how about doing the joint state measurement in an entangled belt states? Entangled belt state is 0, 1 plus 1, 0. That's the basis. 0, 1 minus 1, 0 another basis. 0, 0 plus 1, 1 another basis. 0, 0 minus, this is an equivalent basis. If you do a measurement in this basis, again, you get 4 numbers, P1, P2, P3, and P4. But now the problem is that each of the output is, let's say the result is one of this, that is entangled. So does it mean that the input state is entangled? Even the input state is unentangled, also you'll get output state entangled. Which means, if you want to know the input state is entangled or not, if you do a direct product basis, you will not be able to figure that out. If you do in an entangled basis, also you will not be able to figure it out. Which only means that it is a futile exercise to try to do a measurement on a state, input state, unknown state to know whether it's entangled or not. But on the other hand, if entanglement is there, you can use it as a resource and do some quantum advantage in some operations, like in teleportation or something. Then you know that you're able to do that, means the state has an entanglement and the entanglement has been used up. It is like, I have one currency note in my pocket. There's no way I can check it whether I have or not. But if I give it in an envelope, so if I give it to someone and he gives me food, then I know that I've used it. Then I know that it has non-zero money. So if you have an entangled state which you want to store it, there's no point in storing it, buying it and keeping in storage, because I don't know. if you want to know whether the state is entangled still or not, there's no way I can make out. So it's better to buy the entangled state when you need it. Just before using it, just buy it. All right. Now, next 15 minutes or so, we will actually do a little bit more mathematical and discuss some important things about CPTP maps. Then we can discuss information, visual information, and how the thing evolves. All right. So this is the evolution of quantum states, basically quantum dynamical process. It's also called CPTP map. So what does it mean? So let's say you do a discrete transformation, rho, the state has gone to rho prime. Basically, it's a map. So rho prime is some map n of rho. So this map n maps rho to rho prime. So basically, rho has evolved to rho prime through this evolution map n. Now, this map is called positive trace preserving map. If the output density matrix has eigenvalues between 0 and 1, and trace rho prime is 1, the input is a density matrix, which is trace 1, and the eigenvalues from 0 and 1. Then any map of this kind that will take you to rho prime, which is also a valid density matrix, then it's called a positive trace preserving map. But that's not enough. We need also what is called a completely positive trace preserving map, which only means that you take a joint evolution of rho AB state, it's a joint state, but do a transformation on this state. NA acts on part A, which is like a map, but take you to some other state, but part B, there's nothing you do. It's only identity operation. So which means that in rho AB joint state, I am doing a transformation of state A, but nothing on B. So it will give you rho prime AB. Now, if rho prime AB is also a valid density matrix, that means its eigenvalues are all between 0 and 1, and trace rho prime is 1, then this map NA is called completely positive trace preserving map, or CPTP map. So a CPTP map is a valid evolution map if for all possible rho AB. So though the map is only for A, but it should take all possible joint states of A and B to a valid density matrix. Now, it turns out that all physical observables generate CPTP maps. But there are examples of non-CPTP maps, like transpose map is not a completely positive map. So to do a transpose on A, then rho AB will not become a valid density matrix. In fact, this has been transpose map has been used to detect entanglement. Practically, if a system is n-dimensional, let's say A is n-dimensional, so basically what you do is construct maximally entangled state of, let's say A and also B also n-dimension. Then if the map takes that to a valid density matrix, then the map is completely positive. This is a practical use. Now, some examples is that rho S, let's say system density matrix are about rho S prime of n of rho. If you can write this as U rho S U dagger, means it's a unitary evolution. This is what happens in a closed system. Somebody was asking a question. Like in Schrodinger evolution of a state, it is a Hamiltonian evolution. So state evolved rho prime will be simply U rho U dagger. Now, if rho is a pure state, then rho prime will be pure state. Rho is mixed state. Let's say trace rho square is some number, it will also be preserved. But this in a different basis, they can give different result for parts. Okay, so that means the state itself can be entangled or unentangled. So let's say system has two parts, then you cannot say anything about part A entangled with B or not, and through unit transformation you can change it. So this is how the unitary map looks like. And a non-unitary map looks like this, where you have more than one operator, E1 and E2, E1 rho S E1 dagger plus E2 rho S E2 dagger. And this is a closure, this thing. This is called open system evolution. And this is also called quantum channel in some context. These are the Sudarshan-Krauss operators of representation of a quantum channel. So basically, rho S prime will look like P1 times rho 1, probability P1 with rho 1 state, and P2 is the probability for rho 2 state, and so on and so forth. And every completely positive time preserving map, trace preserving map can be shown to have this representation, Krauss representation. And this is from the Stein-Spring factorization, which has been there for more than a few years now, maybe more than 70 years or so. So there what you do is you start any state, rho s you can always think that is part of a embedded in a bigger state, a direct product state of S and E. So rho is a now combined state of S and E. Now you do a unity transformation on the whole system and environment that goes to rho prime, like U, rho, U dagger. Then if you do a partial trace on rho, then you'll get rho S, and you do a partial trace on rho prime, you get rho S prime. And then there's no reason, no need to believe that rho S and rho S prime are related by unity transmission. So the embedded into an environment, the whole system is evolving. So n qubit state evolves unitarily. That means there's no decoherence for the whole state, but individual spins can be decohered. That means individual parts can get entangled, decohered. So the whole system does not know that parts decohere evolving non-unitarily. That is, whole system is evolving unitarily, but the whole system as a person doesn't know that its parts are actually evolving non-unitarily. Now, one simple example of quantum channel is that take this example. E1 is 1 minus p square root, and then E2 is square root p sigma x. This is called bit flip channel. So what does it do? Rho prime will be p with probability 1 minus p, doesn't change. And with probability p, it changes to sigma x p sigma x. This is what is called a bit flip channel. Now, if it's a pure state to start with, rho is a pure state of this form, you can easily find that the overlap of this state, initial state psi with rho prime is this. It's easy to work it out. So it will be 1 minus p, which is the probability for it to be in the same state as psi. And probability P is a probability to be in the state where you have basically flipped the sigma x flips, right? So it will become, this becomes 1 and this becomes 0. That will be cos square phi sin square theta. So if you do an average of all possible input states, the average fidelity is 1 minus p by 3. Now, the same thing, classical bit flip channel. So classical bit flip channel means what? 0 goes to 0 with probability 1 minus p. And 1 goes to 1 with probability 1 minus p. So which means the fidelity, classical channel fidelity will be 1 minus p. Whereas quantum average fidelity is 1 minus p by 3. It's actually larger. All right. So fidelity only means that output state and input state, how much they overlap. All right. Now look at joint state. AB, let's say both of them are qubits, then the joint state AB can be written as this way. And there's a reason why I want to focus on this. So this is a 4-dimensional matrix. So there's the identity of 1 by 4 because this rho should be 1. That's why it's this. And then PA dot sigma A will be there. So this is a vector polarization that we discussed for qubit A. And this is a polarization for qubit B, vector, basically rank 1 polarization. And now you also have a term of rank 2 polarization, which comes with sigma x of A and sigma y of B, for instance, that comes with QXY. So this is a rank 2 polarization. And these are rank 1 polarizations, which we already introduced. The point is that knowing RDMs, let's say the reduced density matrix of A is what? If I do a trace of B here, since each of the sigma matrices of B are trace 0, so this will drop off. This will drop off, and then here 4-dimensional Hilbert space becomes 2-dimensional. Trace of that will become 1 by half. So this becomes this. So rho A is simply identity plus PA dot sigma A, and similarly rho B will be half plus identity plus PB dot sigma B. So what I'm going to say here is, knowing the reduced density matrix rho A and rho B, you cannot construct rho AB. Why? Because rho A and rho B have no knowledge of this Qij. How, for instance, Qij is non-zero, for instance. So rho A and rho B cannot know whether it is 0 or non-zero, which means joint state cannot be constructed from rho A and rho B, because reduced density matrices of A and B cannot capture the correlations present in the joint state. There is a correlation between A and B, which is represented by this, cannot be inferred from rho A and rho B. Arbitrary local process cannot increase correlations, but can spoil. For instance, rho AB goes to rho tilde AB, which is a direct product of, let's say, U cross UB. Then this is true. That is AB state entropy before and after is same. And similarly, A state entropy is before and after same. But if you do a transformation, which is rho AB, which is not a direct product of UA and UB, then output state A and row AB state and row tilde AB state entropies are same, but row A entropy is different from row tilde A. So which means when you do a unity transformation on AB, which is not a local transformation, then sub parts have different entropies. So you have a joint process. Let's say it's evolving like this, NA cross IB. So row AB has gone to row prime AB. So this actually will involve, because this is a typical quantum channel, so it will involve decoherence of the bipartite state. Now let us ask, let's say this has happened. So what I've done here is row AB has undergone a process on A only, because B part is only identity. So let's say this I've done. Now let us ask whether reduced density matrix of B here and reduced density matrix of B here, whether they're different or same. You can actually go through this. Row prime AB is this, because there's a process only on A, the cross operator depend on only A, and row B prime is trace row prime of A. Then within the trace I can interchange these two, and then sum of this is 1 because it's a CPTP map. So it's the same as trace A row B, which means row B. Which means after this process is done, the state of B, row prime B, is exactly the same as row prime B, row B. So which means no measurement on part B can decipher whether there's a process occurred on A or not. So there's no signaling of the fact that a QDB occurred on A to part B. So this is what goes by no signaling theorem, that while some process is happening on A, it cannot be a signal to other parts. Let's say whether the part is next to you or one centimeter or 1 mile or a million kilometers is the same thing. So this actually is that means the velocity of signal propagation is 0. This is much more restrictive than what Einstein said, that signal speed should be bounded by velocity of light. Here, signal speed is strictly 0. If you have, let's say, two systems next to each other 1 centimeter, also if something happens on A, B cannot make out whether it has happened or there's no signal. As I said before, this happens instantaneously after that, but if there's a state evolves, let's say row prime evolve further using some interaction, then B can make out there's a signal QDP occurred or not. Okay, so now this is what is summarized here. Basically, I'm saying that knowing the reduced density matrix is row A, B, C, there's a part, this whole system is A, B, C, whole state is row W, but then parts are A, B, C. So you cannot construct row W knowing the parts. One more thing is that whole does not know if the part is decoherent. The whole is evolving unitarily, but it doesn't know that the parts are actually decoherent. Similarly, through evolution of a whole, due to a QDP, that's a process on A, then B or C cannot know that actually a process has occurred in the whole. So this is the quantum, the way the quantum system behave. Okay. Now, next few minutes, I'll define a few entropies, mutual information for classical channels and so forth. These are the overlap of two states, rho and sigma is called fidelity. And if it is both are pure states, it becomes simply the overlaps magnitude square. It's like a distance between rho and A. And similarly, another distance you can give is relative entropy. Basically, take trace rho, log rho minus log sigma. It's always positive. It can be proved. Now, quantum mutual information we said is rho AB is S of A plus S of B minus S of AB. It's easy to see that is same as the relative entropy of two states, rho AB and the marginals put together. For instance, let's say rho AB you can construct rho A from rho B, right? So take rho A times rho B. So the distance between these two, that is what is the quantum mutual information. So quantum mutual information captures the relative entropy of joint state and the product state of the RDMs. So which means that it actually captures the correlations present in the joint state. And the important things, sub-additivity, it comes because mutual information, this is non-zero, greater than or equal to 0, which means that S of rho AB is always less than S of A plus S of B. And the concavity property only means that if you take a S of P1 rho 1 plus P2 rho 2 is always greater than or equal to the average entropy weighted with P1 and P2. All right. So the next few minutes, what we'll do is look at the classical information. So information is always is neither classical nor quantum. Information is what you seek. Let's say I want to send a message, let's say from here to here, let's say the receiver. So what I'll do is the messages, I'll do some coding, and then the code such that there'll be so many bits I have to send. So so let's say some number of bits I have to send. Each bit I'll be sending through a classical channel N. So X is the bit, let's say I send, and then through the channel, and maybe because of the channel action, then the bit is sent Y. For instance, let's say I'm sending a bit in 0, it becomes 1, and so on and so forth. Now, the receiver will receive, and then it will decode, and then it will construct the messages. If the channel is not noisy, then all the information I sent here will be constructed back and will messages. So when you say classical information, basically is that I'm using classical methods here. When I say quantum information, it's exactly the same thing. Messages here and messages here, which have to reach there. But quantum only means that I'll deal with the qubits here, and they'll go through quantum channels, and then I'll go to do measurements on that. So when somebody says quantum information processing means, it's not that information becomes quantum. It only means that I'm using quantum objects to actually for communication protocols. And the source is basically Q of X with X. The X will come with probability Q of X. And receiver is receiving Y with probability, a conditional probability that you're receiving Y, given that X has taken some value X. That's called conditional probability. So then, so conditional probability, you can concept the joint probability. Probability Q of X times this conditional probability of Y within X is what is called the joint probability. This is from Bayes' rule. Now that you have P of XY, I can get Q of XY, Q of X already I have. Then by doing it marginal on of Y here, that is trace over X, then I'll get RY, which is the marginal Y. So now from here I'll get H of X, from here I'll get H of Y, and from this I get H of XY, and Shannon entropy is this. H of X plus H of Y minus H of Y. All right. So the same thing I can do in quantum also. But as I said, here, this is the classical classical information of a quantum channel. What I'll do, I'll prepare a state, let's say in this source, prepares a state rho X with probability Qx, and so on and so forth. This is the process. So you have Qx1, X2, so many of them. And then receiver will receive that bit, and you'll do measurement in some basis, and you'll get a probability Y, and probability, joint probability C Y of X in exactly the same scope. So basically, a density matrix is sent here, rho 1 is sent, and here you'll do a measurement in some basis, and you'll get this. So finally, you'll get again Shannon entropy, H of X plus H of Y minus H of X 1Y. So this is the classical mutual information of a quantum channel. Now, this is the key here. You have a communication channel. Now you can also define a quantum mutual information quantum channel. What you have to do is, classically I said that X goes to Y through N. Then the capacity, channel capacity is defined by, this is the source coding, the channel coding theorem. So the maximum of IXY, the mutual information between X and Y, I calculate for, and then maximize with respect to all possible input distributions I have. Then that is the capacity, channel capacity. Now, quantum channel, what you have to do is construct joint pure states A and B, and then let B go through a quantum channel. So let us say I construct phi AB is a pure state, and then let it go through a channel, and this channel is only on B, let's say. I is for A, which is a identity operator. Now it will become a density matrix OAB, joint state. Now, what you have to do now is that take the quantum mutual information IAB, which is S of A plus S of B minus S of AB in the state rho that I calculate, and maximize over all possible phi input states. And this is what is called the channel capacity or mutual information of the quantum channel. And as I said, this sort of things are not easy to do. For some channels people have done. Now, private information of a quantum channel. So remember we said there's some wiretap channel. In the classically you say that you have a compromised classical channel, which means that I'm sending a number from X to Y through the channel N, and then somebody is intercepting, some eavesdropper, and then gaining the information called Z. Right? So then the information gained by, let's say, B at from Y is not private, because there's a mutual information IXY minus mutual information XZ, which is non-zero. Then the difference, which maximizes over all possible input, that is what's called private information. which means the information gained by the mutual information gained by the eavesdropper, basically that is mutual information between X and Z. You have to remove it from there. So in principle, this will be less than the channel capacity. So this is what is called a private information. Now the same thing I can do in quantum. What I do, I'll start with a classical quantum state. For A, I took a diagonal state with probability pi, and then B state is rho IB. Now let B go through a channel. So N acts only in B. So then you'll get a sigma matrix, density matrix. Then sigma density matrix, you can always think of in terms of purification. Remember, this is a joint state of AB mixed. I can always think that there's an environment with it. So I'll think that it's a pure state ABE, phi ABE. Now, private information of a quantum channel is that from this state, I calculate AB, that is density matrix of basically the information, mutual information AB, that is IAB, and the quantum mutual information AE also I can calculate from here, that is IAE. The difference in the state phi, now I have to maximize all possible input states. This is what is called the private information of a quantum channel. Exactly the way we have done for the classical case. Now, since time is less, I have another this thing. This is a data processing inequality. For classical channels, let's say X goes to Y due to noisy channel. Let's say N1, X has gone through N1 and gone to Y, and then Y has gone to the other channel N2 to Z. Now, basically, the mutual information between X and Y and X and Z. It can be proved that the mutual information between X and Y is always greater than or equal to mutual information of X and Z. That is because there's a further channel. So that means any noisy channel will decrease mutual information. So correlations are contained in PXY, PYZ, and that determine the mutual information basically. So correlation between X and Z deteriorate because of this noisy channel. So quantum state, you can do similar thing. What I do, I start with the phi AB, let it go through a channel, B is going through N1, then it will become rho state of joint state AB, and then it will go to another channel for B and it becomes sigma state. Then you can easily prove that the mutual information in this state, IAB, phi, is always greater than or equal to mutual information AB in rho state, and is always greater than or equal to mutual information in this sigma state. Namely, when this pure state goes through, let's say, one channel, I cross N, then mutual information between A and B will decrease, and goes to another one, it decreases further. So quantum correlations between A and B keep deteriorating due to quantum noise. So thank you for attention. I've already, some questions are there. Let me go through these questions. Okay, Soumik, we already answered. Hello, sir. This is Surya from Hyderabad. MSc physics students are eligible for doing quantum technology course, and what are the job opportunities I have in this course? This question is best answered by other experts who have been speaking, who have knowledge about the field and the technology, how is being implemented, and what are the potential growth and so on and so forth. There's certainly some opportunities exist, and you should talk to the other experts who have talked about this. Okay, we are answered already entanglement and correlation. We are answering. Kamalesh from Karimnagar. My question is, how does C0 get work? We already answered that. Tanish from Nalgonda. Any relationship between mechanics and quantum information, mathematics and quantum information? Yeah. So the point is, the quantum information deals with linear vector spaces, right? So to the extent you have to have mathematical background. And then mathematicians working on this, they work on mathematical problems. For instance, just now I was saying how to say private information of quantum channel. To calculate that, you need a lot of mathematics. Navanita from Kalvakurti. My question is how quantum information is used for. Okay. So there are certain advantages using quantum. Somebody was speaking of quantum cryptography the other day, and many other things. Quantum entanglement is also used for doing many operations. For instance, you want to do a teleportation of state. If you have entangled states, you can do this. Okay. So there are a lot of algorithms, protocols have been developed. Okay. Keshav from Kamaredi. I'm from computer engineering background. Could you suggest a software platform for the simulation of quantum computing and quantum information? Yeah, there actually exist several of them, and you can contact some people who implement them. Hopefully some of the speakers actually will give you some links. Ramya from Islamabad. Is there any probable applicability of quantum computing in artificial intelligence and machine learning? Of course, there is a possibility for everything. So every problem which can be solved on a quantum classical computer, if it becomes very, very difficult to solve because it's time consuming, can be done easily on a quantum computer. That is a promise. So what it can do cannot be said, but promise is that you will get a speed up. So time consumed will be less, and also some problems which may not be able to easily formulate on classical computer also can be done. I hope I've answered questions.
Sir, I believe there's still one more last question left.
Many people work with quantum field theory. Some of them also look at quantum information theoretic aspects. Okay, so these are actually these concepts are much more involved than what simple things that we discussed. So what we in this talk, what we can focused on is simple ideas of 1 qubit and 2 qubit, how the state changes, and what do you mean by information, and how to implement that, and things like that. Yeah, there's certain approaches are there from quantum field theories also about quantum information theory.
Priyanka garu, are there any more questions from students?